Good morning and good afternoon, everybody. This is Mike Nieberg. I'm Vice President of Business Development here at Noesis with the Optimus software, and we really appreciate your time today. I'm really excited about this particular subject, mesh morphing with Sculptor along with design optimization with Optimus. It truly represents a leading-edge approach which has really enormous potential benefit for CFD users. So we're going to wait just a few more seconds. We see that there are quite a few people signing in right now. So if you can just give me about 15 seconds while we let those last people sign on. Okay, the agenda that will follow today will be fairly straightforward. I'll do a 10 or 15-minute introduction into Optimus. And then we'll be followed by Mark Landon. Dr. Mark Landon will be doing a similar introduction of Sculptor. We will then go to perhaps the most interesting part, which Taylor Newell will be delivering, which is a case study along with a live demo showing both packages actually working, showing Optimus working. And we hopefully will have a few minutes left over at the end for a Q&A session. We have a very large audience, so unfortunately we have all of the microphones muted, but you can type in your questions in the little control box. You'll notice a question section. You can type in any questions you have at any time during the presentation, and at the end we'll be going through those questions, and if we don't get to them, we'll certainly be emailing you a response back. For my Optimus introduction, my goal here is to begin to give you hints on how you can derive much greater value from your multidisciplinary simulations. And what you'll see is that with Optimus, you'll delegate repetitive, non-value-add work to the computer. You can simplify your design work by focusing on only those parameters that are important relative to one another. It also allows you to focus on just the feasible designs, which becomes particularly important, for example, if you're doing a multidisciplinary type engineering effort, one that might involve, as an example, structural analysis and CFD. This ensures that you're focused on feasible designs for all the different types of simulation or engineering requirements. Maximize efficient use of your simulation resources. With Optimus, you can use a strategy that combines meta-modeling, which we'll go into more detail, as well as direct optimization. And we'll describe that and show that to you in much greater detail so you can fully appreciate what we mean by that. Consolidate simulation knowledge, referring back to the meta models, which, by the way, are also called response surface models or surrogate models. Sharing those with other engineering teams through an easy-to-use interface. What we're talking about here is being able to create working models that don't require the underlying simulation to run anymore. So if you're doing CFD and structural analysis, you can quickly transfer a model that will give an engineer the results of any combination of inputs within 1 second with no requirement to understand how to use those underlying packages. So this is quite a powerful capability that Optimus will give you. Optimus actually has a variety of different functionalities, all working together to help you to arrive at your best designs possible in the given constraints of time and compute facilities. The ones I'll talk about, the primary ones here, are process integration, design of experiments, response surface modeling, optimization, and robust design optimization. So starting off with process integration. Process integration is the capability that Optimus provides that allows you to link any number of different programs
So you could, for example, as in this case, you could have a CAD package, you could have several different types of simulation, CFD, structural, MATLAB, in-house codes, and so forth. Just about any package can be linked. These are all run in one single automated workflow. So this by itself can become a very substantial help. You can run kind of a batch mode overnight, over weekends, getting many different processes completed. You also have quite a bit of control with that workflow. So you have embedded logic systems that allow you, for example, to filter designs. You may have a very quick and dirty first look through, let's say, an Excel program, and when the designs are acceptable, those are passed on to do a full high-fidelity 3D CFD. So there's a lot of control that you'll have. It also overlays your IT infrastructure and will allow you to make use of parallel processing, HPCs, local network-based software and files. So process integration by itself can shave many days off of your work. Perhaps more importantly, you're not going to have to be there for each step in between the way. Next capability is design of experiments. DOE, something that I'm sure many of you are very familiar with and using, is very critical to the optimization process for two reasons. The first one, which I'm showing you here, is the rapid identification of key design variables. On the right is a picture. This is a 1D package simulating a diesel fuel injector valve. Design variables in this case were some diameters, which you'll see in blue and red, and a poppet half angle, which is the yellow, which is that little triangular section. What Optimus will do is run a design of experiments using a variety of different very efficient techniques to ensure that your design space is very well captured with a minimum number of sampling points, and then do a statistical analysis. So on the left is a chart. It's one of the many different types of post-processing available. This chart is very valuable because it allows you to quickly identify which input parameters are most important relative to how they impact the output, the solved quantities. So the first four, if you look on the left-hand side, duration, hole diameter, poppet half angle, and then you look across, you see the color coding and the numbers. A very high correlation is red, a very low correlation is blue, and then in between are the other colors. What is, in this case, extremely interesting, if you look halfway down to poppet half angle, and you go to the right, you'll see that it has negligible impact on the different objectives or output quantities, the last three that are shown. So in this case, the poppet half angle can be fixed to the least expensive design. It can also help you to reduce the complexity of your simulation, which of course will be very important for CFD, where eliminating any design variable can help speed up your runs. So this sensitivity and ranking of the different input variables is exceedingly valuable, especially if you have a large number of parameters and you don't know where to start. It's also used in a completely different way, which is in the creation of a response surface model or meta model, which is actually called a number of different things, surrogate model or approximation model. Here, what Optimus does is it interpolates a continuous surface from the DOE discrete samples. So you now have a mathematical surface representing all of your responses or results of your various simulations. And with that, you can now put in any input, any combination of inputs, and immediately, as in less than 1 second, identify what the outputs should be based on this mathematical fit from your DOE. This is also portable, so you don't have to have Optimus. Indeed, you don't have to have the underlying CFD or whatever types of simulation were used to create it. So another engineer can now run this and look at different combinations of inputs and determine immediately what the theoretical output would be. In the optimization strategy, it becomes essential because you can now do an optimization on that surface and identify the key or best designs, and then go back to high fidelity 3D modeling just in that region, or you can do experimental work in order to validate and perhaps squeeze out even better results. Now let's move to optimization. You've done your DOE, and you're now ready to go to direct optimization, which is a sequential process. By the way, DOE, one of the nice things is you can run that in parallel. But with direct optimization, it can't be run in parallel because each design is changed based on results from the previous design. So just to show you, to illustrate how and what Optimus is doing for you, we have this truck on the right, which is actually taken from a real truck work we were doing with Navistar. And the geometry was proprietary, so that's why you see a rather ugly, blocky looking truck, but this will nonetheless show you what's going on. With the optimization algorithm, the first thing that it does is it actually performs a design of experiments. So like you, the optimization algorithm needs to understand the relationships between the inputs and the outputs, and cover that design space. So there are a lot of hidden mathematical relationships that can't be understood necessarily by a human, which are mathematically determined. And then it automatically proceeds to the optimization algorithm, having been armed with the knowledge from the DOE, and very efficiently progresses down to the best designs. So you'll notice that in this latter two-thirds, there have been very direct convergence to the best designs without having to sample into the high drag region. So it's found the trend, the right trend, and is very efficient about focusing the simulation efforts. In addition, other information that you derive from optimization, in particular multi-objective optimization, where you have more than one objective, and the case that we showed, in fact, was drag and volume, you often have a resulting trade-off curve. So what Optimus is doing is, if you start from the baseline, you have a design that's very low in volume and very high in drag. The truck, by the way, we were trying to minimize the drag while maximizing the volume of the cab, the rear section where the driver can sleep. And these are competing objectives, as you can imagine. So you have your baseline case, you have a DOE which identifies the best design just on that DOE, but further refinement reveals a trade-off curve which is called a Pareto front, which are all the designs that run on a continuous curve here with just two objectives. So you have a volume drag trade-off, and now you can pick the best design depending on how you weight those different objectives. And of course, this could be 10 objectives or many more, and we have different graphics to help you deal with multi-dimensions.
A few words about our company. Noesis has probably about 17 years of experience now in developing Optimus since its first release. We are the largest OEM provider of embedded optimization. What I mean by that is we actually provide optimization algorithms for third-party software. They have what I would call simple in that it's no interaction with the user, but it's very complex in terms of getting a robust technique to give optimal or DOE solutions. That gives us a lot of experience with the different optimization algorithms. They have to be robust. We are the leader in this field. We have a larger installed base than any of our competitors, with over 2,000 companies using the embedded solutions or Optimus. And our worldwide presence continues to grow here in the U.S. We're outside of Indianapolis. Our home office is in Belgium, and we continue to open new offices, most recently Israel and India. Our customer base is quite diverse. We are the dominant player in the automotive industry, used by almost all the major automotive companies in Japan and Germany and elsewhere. We're also quite widely used in the aerospace industry, and over the last 5+ years, increasingly diversified as anybody doing simulation can benefit from this. So I've rushed through a very quick introduction of Optimus. I hope that it's given you at least an initial feel for how it may be used to allow you to get more out of your CFD. The process integration can automate, the DOE can provide sensitivity, the response surface models give you a very fast approximation without having to run CFD, and then optimization itself can get you those best designs. So I'm now going to turn it to the next presenter, Mark, who is going to talk about Sculptor and the mesh morphing aspect, which is almost like icing on the cake. It's a fantastic combination. So Mark, you can unmute yourself, and I'll hand the control over to you.
Thank you, Mike. It's a pleasure to be here and give a presentation on an introduction to Sculptor and a little background on our company, Optimal Solutions. We're pleased to be working with Noesis and their tool Optimus. Optimal Solutions is the name of our company, and Sculptor is the name of our tool. Our largest capability in our tool is called Morphing, and it's our proprietary tool is arbitrary shape deformation. It allows the user to create their own user-defined shape change parameters on the mesh. And so we consider ourselves shape optimization experts for CFD, FEA, and multidisciplinary optimization. We can handle both internal and external CFD models, structural mechanics, and we can even do arbitrary deformation of CAD models in the same fashion. We also offer some consulting services. Some of our early adopters were in the motorsports, especially the Formula One teams. Sculptor has enabled them, based on one of their leading aerodynamicists, to get their aerodynamic components designed and optimized easily and quickly finding the improved gains with arbitrary deformation. Morphing, our ASD technology is very smooth, volumetric, and provides the shape changes for these different geometric models. It's interfaced with most commercial and government formats, including Star CCM, OpenFoam, Fluent, CFX, and many other CFD tools, as well as ANSYS, Abacus, Nastran in the finite element area, and soon we'll have other formats as well. As far as CAD, we can read and write STEP, IGES, ACES, SAT, and Parasolids. Well, Sculptor provides the parametric shape change variables where the user defines his own group of these ASD control points, but allows him to change the shape without going back to CAD to remesh. So it saves a lot of time by operating on the mesh rather than in the CAD. You can define variables to rotate, scale, or translate groups of control points where each control point will have its own vector or curved spline to move. We have found that it's almost always the small, subtle shape changes that help provide the big gains in their physics-based performance. Often the result is a non-intuitive, improved design. We also offer batch mode so that our morphing capabilities can be included in optimization algorithms such as Optimus. A few examples. One of our customers, Gulfstream, builds business jets, and they're working on bringing back supersonic flight. Sculptor has helped them explore the designs that help mitigate the sonic booms for better designs. Other aerospace examples, and these are just a few, whether they're looking at turbine blades or nacelles or wings or thrust reversers, Sculptor can help them improve whatever design objective they might have for their aerodynamic performance. We are also big into motorsports, automotive, and trains. We helped Brigham Young University develop a streamliner, an all-electric vehicle, and the shape helped them achieve a world record for an electric, all-electric car last year. We can help optimize the shape of trains and cars. This video you see on the bottom is actually a screen capture of how Sculptor performs the deformations. They're very smooth and they're in real time. So the change to the mesh is instantaneous. For internal fluid flow and shape matching, many of our customers now are looking at Sculptor to help do shape matching, where they can morph one shape into a target shape, where the target shape is a different shape, maybe just slightly different. But this allows people to reuse a good mesh that they have created on the as-designed part, and they're able to analyze an as-built part. Being able to improve mass flow, or reducing pressure drop, or improving the flow quality inside of a duct or inside of a combustion chamber is also important. In structural design, using finite elements, we can help minimize stress concentrations or mitigate fracture mechanics and things like that. We could also help mitigate vibrations, such as changing the shape slightly of a turbine blade so that it does not vibrate at a resonant frequency. And in the lower right, we could help optimize say a penetrating projectile. Also, fluid structure interaction down on the lower left is important, where we can morph both the structural FEA model and the fluid dynamic CFD model with the same shape deformation to look at fluid structure interaction. Sculptor's GUI is full of other useful features, such as allowing instant creation of many different designs, starting with just one mesh. New ASD volume creation tools for creating these shape change volumes can be used so that it doesn't take very much time at all to create a complex deformation. I'm going to show you a video here in a moment how that is actually done. We also have cell quality dialog to keep track of the cell quality as we deform. Of course, we're going to change the shape of the cells because we're moving the nodal points around, but we can keep a track and still keep good, high quality cells through a deformation. Traditional optimization with CAD in the loop requires you to either automate the remeshing process, and even with the best of tools, that can still take time and need user input. But going to the solver post-processing and then going back to CAD, that can take a lot of time that could be better spent looking into your optimal design space if you could automate that shape change outside of the CAD loop. So that's what Sculptor does. Sculptor allows you to automate and optimize the solver and morphing loop. And then with Sculptor, we can always take that final optimal shape on the mesh, apply it to the CAD model, and get it back to the CAD with one deformation on the CAD model. Here is a video just showing you quickly how to quickly set up an ASD volume, which is a trivariate parametric entity with control points. And then these control points are simply moved to perform a deformation. In this case, we are creating cutting planes where we place a set of control points and then automatically shrink those to fit right on the surface, both the top surface and the bottom surface of this blade. And with a few mouse clicks, you can move the control cutting plane and create another slice and another slice until we have enough control points. In this case, we want to set up a shape change variable that will create a notch in the leading edge. I'll let Taylor next discuss how that notch is going to be affected for the design optimization that we're looking at here. But just to set this up, we quickly create these surface control points, and then we go to the next step of creating a far field set of points that give us the ability of the surface control points to smoothly morph the shape out into the flow domain, so that the flow domain remains a high cell quality mesh for the subsequent calculations in the CFD solver. Let's just take another minute to finish up these steps. But this is the sculptor interface allowing the user to set these user-defined shape change variables. It would be nearly impossible to create these type of real-time deformation variables using the CAD parameters. So with just a few clicks of the mouse, it's creating the far field below and above and before and aft of this turbine blade. And the very next step then is to create a user-defined group of several control points that will actually mimic the shape of a notch or a nick that would be caused by foreign body damage. So this is the last step, is just to create a user-defined group here to actually control the deformations. So these user-defined groups then become design variables in the optimization process. So this closes the loop between the meshing and the optimization that Optimus will perform as we set this problem up to become a automated shape optimization problem. So just to test this variable out, make sure it's doing what we want, and there it can create a deformation of that leading edge to create a notch. I will turn the time over to Taylor Newell now, who will continue this discussion how Sculptor and Optimus are linked together to solve this problem.
Excellent. Thank you, Mark. We'll get my presentation started here, and everybody should be able to see my screen. I'd again like to echo what Mike and Mark said and welcome everybody to our webinar this morning. And what I'm going to do is really pick up where Mark left off and show how the rapid deformation and morphing capability that Sculptor has can be harnessed as part of a process integration and design optimization workflow that Mike introduced. So, and we'll use that to quickly generate a design of experiments, run an optimization, and then ultimately distribute that information about the CFD analysis to a much larger audience so that you're really able to get much higher value out of the analysis that you've run, or the analyses that you've run. So throughout the case study that we'll show you today, we're going to demonstrate really how Sculptor and Optimus can help save you time by removing the need to recad and to remesh for each design change, and how an automated workflow can reduce the amount of user input that's needed for complex tasks. We'll show you how using Sculptor and Optimus can help you improve the performance of your products by making subtle shape changes to your geometry, and by using Optimus's intelligent optimization methods. And then finally, we'll show that you can use Sculptor and Optimus to consolidate the knowledge that you're able to gain from the optimization and analysis cycle. You can then, as I mentioned before, distribute that intellectual property through Excel so that non-CFD users can access and create new simulations quickly. As Mark alluded to, the case study that we'll show today focuses on blades. These blades are generally located inside of a jet engine, as you can see in the top image. These blades can get damaged from a number of environmental sources. There's over 26 million blades that are in use throughout the world today. A great deal of time and money is spent repairing damaged blades. And so when these blades are damaged, what's called a blend is used to fix the blade. So it's really imperative to determine the maximum amount of damage that a blade can have and still provide enough lift force to keep the jet engine in balance. So as Mark mentioned, here are a few examples of damage that can occur to these blades. So the damage is referred to as a foreign object damage, or FOD, and it's generally referred to as a nick. So that's what we'll be talking about and simulating today. So our goal in the case study is to simulate the FODs that occur on the blade and to calculate the aerodynamic lift force so that we can eventually find the largest nick that a blade can have and still provide enough lift force to keep the jet engine in balance. The process that we're going to go through in order to do that is that we'll first determine the input and output variables that are needed to control the blade and to also get the information that we need from the blade. We will then use that information to create an automated workflow inside of Optimus. That workflow will drive a design of experiments, and then the DOE response data will be used to create what's referred to as a response surface model, or a mathematical approximation of our design space. We'll use that response surface model as part of an optimization that will run much faster than the original design of experiments ran. So from all of that, we will generate some, or we'll consolidate some corporate knowledge so that we can distribute the intellectual property about the model to a large number of users that otherwise would not have been able to access that data. So as I mentioned, the first step is to determine the variables. So we have input variables and output variables, obviously. And as you saw in Mark's presentation, he's used the arbitrary shape deformation ability of Sculptor to create or to simulate nicks that occur on the leading edge of the blade. And so what we've done is we've actually created 4 separate nick locations along that leading edge, kind of growing in a radial direction, or excuse me, in an axial direction along the blade. So those will be our input variables, those 4 different nick locations. So and then the output variables, the information that we need to get from the analysis, from the CFD analysis, is the lift force that's being generated by that blade. And then also from Sculptor, we will calculate the volume of the blade. So our next step is to determine the workflow. We first want to change the geometry, calculate the volume, and then export the morphed mesh. After that, we want to determine if the mesh quality is good enough to allow us to run a simulation. And then finally, we want to solve the model in our CFD analysis tool, and then extract the outputs from the reports that are generated by the analysis tool. And for this optimization, we've selected Star CCM Plus as our CFD analysis tool. Optimus has built-in dialogues for CCM Plus and really all the other numerical analysis tools out there, including Fluent and CFX, OpenFOAM, and even in-house codes that are developed internally. So the dialogues that Optimus has generated automatically detect both the input and the output variables that are inside of the input files for the CFD tools. And then Optimus, of course, also has built-in dialogues for Sculptor that we'll use. So now we'll show the workflow as it's actually been created inside of Optimus. So you'll remember that the first step was to change the geometry, calculate the volume, and export the morphed mesh. So here you can see the call to Sculptor, kind of in the middle of that image there, and then the green boxes that are the input and output files that Sculptor needs to make the deformation. The teal box, or the teal oval in the upper left, is actually the input variables that are used to make the changes to Sculptor, to the blade inside of Sculptor. And then the red shape at the bottom is actually an output variable that comes from one of the Sculptor logs. And in this case, it's the volume variable. Now, the next step is to check the mesh inside of CCM Plus to determine the quality. This could have been done, as Mark said, inside of Sculptor, but we added this extra step to do the check natively inside of CCM Plus. And finally, if the mesh quality is valid, we're actually able to use Optimus to make a decision about if we should move forward with the analysis or if we should generate a fail condition. So, and then finally, the red oval in the bottom right is where we extract the outputs from the CFD analysis logs. Now, after we've automated the workflow setup, we're actually ready to begin the design of experiments. So the reason that we need to define a design of experiments is so that we can, in a statistically relevant way, cover the entire design space. So we need to cover the entire design space with experiments so that we can create the response surface model that we've been talking about. So this will all help to support the design exploration down the road. So for this case, we've actually determined to use the Latin hypercube design of experiments method. Inside of Optimus, the Latin hypercube is one of about 20 different DOE methods, including a full factorial method, a custom adjustable factorial method, and a Monte Carlo method. Now, we ran the DOE. Each of the individual CFD experiments took about about an hour to solve, and we ran 100 different designs as part of our DOE. So here you can see the results of those 100 experiments. You'll notice here that there's really good input distribution amongst the input variables, the FOD 1, 2, 3, and 4. And as well, you'll notice that some trends are beginning to emerge in these two columns, which are the volume and the force output columns. The chart on the right shows both the lift force response for the baseline geometry in green there, and then the response for each of the additional 100 experiments in blue. Now, the video that's being shown on your screen is actually a video that's exported from Sculptor, and it shows each of the different deformations that were part of the design of experiments. So these are all 100 designs that were tested inside of our CFD tool. So from all of this response data, we're actually able to generate some correlation. Using tools inside of Optimus, we were able to find the influence that each input variable had on the output variables. And in addition, we were able to find the correlation that the output variables had on each other. So we've identified that FOD, the variables FOD2 and 3, had the strongest correlation with lift force, and that FOD1 and 4 had the weakest correlation with lift force. The correlation, though, or the influence that FOD1 and 4 had on the lift force was still relatively high. You'll notice that it's not that many points off of FOD2 and 3. And so unlike in the example that Mike showed earlier, for the optimization, we actually won't be able to exclude any of the 4 input variables. So we need to keep all 4 input variables as part of our optimization. So in addition, we did notice that the lift force and the volume output variables were highly correlated. So if you're keeping track, the next step in our process was to create a response surface model from the data that we've generated, or from the DOE data that we've generated. Now, a response surface model, for those of you that may not be familiar with it, is simply a mathematical approximation of a set of data points. Most have used the add trend line function in Excel to create a mathematical approximation of a two-dimensional data set, as you can see on the screen here. The trend line equation that we've all added to the chart in the past is, in fact, the mathematical approximation of the data. Optimus has the ability to quickly create a multi-dimensional mathematical approximation that includes multiple inputs and outputs. Obviously, it's a little more difficult to visualize than the 2D mathematical approximation here inside of Excel. So I'm going to switch over to Optimus now, so that for the first time you can see the user interface of Optimus. Here we can see the response data from the 100 design of experiment runs that were calculated, the volume and the lift force there. And now, as we'll show, we can create that response surface model with 2 clicks. So we'll select the type of response surface that we want. In this case, we'll do a radial basis function as the formula to calculate our response surface, and then simply click Apply. And here in about 5 seconds or so, that response surface will in fact be generated. So it took 8 seconds, excuse me. And now you can see it shows up in our tree as Model 1. We can then visualize this response surface. So as I mentioned, it's not the simple line which we had in Excel, but it's actually a much more complex surface. So this is, in fact, the response surface model that's been generated. So there we're comparing outputs, here we're comparing the lift force output to the FOD1 and FOD2 input variables. So we mentioned before that FOD3 and FOD4 had the FOD3 and FOD2 had the highest influence on the lift force. So here we can see the response surface that's generated from that data. Now the beauty of this response surface is we can now calculate points along this surface much faster than we could by going out and calling the CFD analysis tool. So here we'll just run 100 new experiments. So these are experiments that have not been previously solved in the CFD analysis. And we'll run these experiments, and you'll see that in just a second, 100 new designs were able to be calculated. So for the optimization, we want to find the largest NIC that can be created that will still maintain a feasible lift force. So Optimus, again, has a number of optimization methods, but we've selected the simulated annealing method due to its ability to cover the optimization path extremely well and test for a global optimum. We've set a constraint on the lift force at a 1% reduction in the baseline lift force, and we want to minimize volume, which essentially allows us to find the largest NIC that we can deal with, that we can have. So here you see the progression of the optimization. So the actual optimization took less than 2 seconds on that response surface model. And you can see that we were able to quickly converge on an optimal solution. That is the pink vertical line in the chart. we were able to reduce the volume by about 4 points, which is much larger, actually, than we expected. So, and you'll notice also that the optimization actually went beyond the constraint in order to determine if a global minimum had been identified. And here's the resultant geometry that was created for the optimal solution. Now, the next step in our process is to consolidate corporate knowledge. So the concept here is now to allow other non-CFD users to access and extend the data that was calculated with the DOE and the optimization. So Optimus allows the users to export the response surface from Optimus and load it, in this case, into Excel. So here you can see that the user has defined, I think we've got 30 unique experiments inside of Excel. This is the data that you see in the red column. These experiments are ones that were not previously calculated in the CFD tool. And I'll just make a few changes to these experiments. Then the user simply has to hit Calculate. And Excel will, using the Win32com app and connecting to that exported response surface, call the response surface model and generate the results that you can see have occurred. And then we've plotted them here. So any Excel dashboard could be made here to interact with that response surface model. All right, so what have we seen here? Let's discuss the impact a little bit. So without Sculptor and Optimus, the design of experiments and the optimization would have taken about 17,000 minutes. With Sculptor and Optimus, it only took about 6,300 minutes. So over 150 hours were saved. And here's how we got those. Here's how we got those numbers. You can see obviously some significant time savings in the creation of the geometry with Sculptor, removing the need to recad and remesh, and then also in the simulation time during the optimization step. And really, this process would not have been possible without Sculptor and Optimus. It would have been impractical to make all of those design changes, and it would have been impossible to drive the optimization and to export the data to Excel when we were done. So we've shown now that with Sculptor and Optimus, over 38 man-hours, or a week of time, was saved. And with Optimus, over 140 computer hours simulation time was saved. And Sculptor enabled the generation of thousands of different designs, really. And then Optimus found the maximum acceptable FOD. And ultimately, we showed how the simulated designs can be extracted or can be changed by non-CFD users inside of Excel, and the complex CFD models were able to be solved in seconds. So in conclusion, with Sculptor, we removed the need to recad and to remesh, and we were able, with Optimus, to determine the maximum FOD size that we could have. And then finally, we were able to get non-CFD users fast and easy access to the data. So thank you so much for your time.